Welcome everyone. This is Professor Richard Holowczak, and this is the Concurrency Control Lecture. If you have not done so, please review the Transaction Processing Lecture before continuing on. In the Transaction Processing Lecture, you will learn about transactions, ACID properties, transaction processing problems, transaction schedules, and serializability. What is concurrency control? Concurrency control is part of the database management system software that controls when a transaction can proceed to read or write some data. Reminder that all transactions are isolated from one another, and this is the I in the ACID properties. If concurrency control is done properly, the resulting schedule will be serializable. This means that the schedule will run very quickly, transactions can run in parallel, and the schedule will be free from transaction processing problems. There are several concurrency control approaches, including locking, timestamping, multi-versioning, and optimistic concurrency control. This video will focus on locking. What is locking? Before a transaction can either read or write some data, it must obtain a lock on the data. It's a bit like holding up a flag that says, I'm about to work with this data item, and other transactions should stay out of my way. They should not be allowed to touch it while I'm doing my work. This is very much like a semaphore or a mutex that we find in C++ or Python programming. Operating systems also have this concept, and it's used to protect files, shared memory, and other shared resources running on a computer or a server. There are three general characteristics of locks. First, locks can be placed automatically by the database management system, and this is what happens most of the time. A transaction is submitted to the database management system, the concurrency controller takes a look at the work to be done, which records will be read, which records will be written to, and will automatically apply the necessary locks. Occasionally, if a large amount of data needs to be worked on or updated, the programmer can manually place some locks. They can write some specific programming code that says, I'm going to lock the entire employee table, for example, and no one else can touch it until I have updated everybody's salary. And then the programmer will have to manually unlock that table. The second characteristic is called lock granularity, and it asks the question, what is being locked? Locks can apply to a single row or record in a database table. It can apply to a page, or what is sometimes called a block, which is a collection of records. A lock can be applied to an entire table, or a lock can be applied to an entire database. Most database management systems will lock a page or a block of data at a time. The third characteristic is what is the purpose of the lock? Locks can be used for exclusive or shared access to the data. And in general, when a transaction needs to write or change some data, it must obtain an exclusive lock, and we designate that with the letters XL. When a transaction only needs to read some data, it can obtain a shared lock, which is abbreviated as SL. So who places the lock? What is being locked? And what is the purpose of the lock? Those are the three characteristics of locks. The most commonly implemented method of locking is called the two-phase locking protocol. Two-phase locking has two phases. In the growing phase, a transaction acquires the locks it needs for the data items it will work with. So during this growing phase, the concurrency controller looks at the work that the transaction has to do, which records will be read, which records will be written, and it helps the transaction to get the locks on those items so that the transaction can proceed to read and write data. The shrinking phase happens once a transaction releases any lock. Once a lock is released, the transaction cannot obtain any more locks. And this is a very strict rule. Even if a transaction releases a lock and wants to get the same lock back, it cannot happen in two-phase locking. You have a growing phase, and then as soon as one lock is released, the transaction enters the shrinking phase. If every transaction follows two-phase locking, then the resulting schedule will be serializable. The following diagram illustrates how a transaction acquires and releases locks over time. The x-axis, we have the lifetime of the transaction. It begins on the left and it commits over on the right. On the y-axis, we have the number of locks that a transaction will acquire as it does its work. As you can see, when a transaction gets started and applies the first lock, it is in the growing phase. As it acquires additional locks, it will continue growing and adding more locks. At some point, the transaction will have acquired all of the locks that it needs to do all of the work. That is, all of the data items that it needs to read and write. As soon as one lock is released, now the transaction enters the shrinking phase. And notice the transaction cannot go back and get any more locks. From that point on, the transaction can only release locks until it reaches the commit point. So this little tip at the top of the triangle here, this is the inflection point. As soon as a transaction releases a lock, it moves to the shrinking phase, and that's it. It cannot go back and get any other locks. If you look at this diagram, it shows a violation of the two-phase locking rule. In other words, a transaction got all of these locks, released one, but then it went back to get another one. Once that happens, this is a violation of two-phase locking, and it's not allowed. So you will never see a shape like this in a two-phase locking situation. Transactions can acquire locks and they can hold them for some time while they do their reading and writing. So this shape can be slightly different. Here we have a transaction that acquired a bunch of locks over time, and then it held on to them for a while it was doing its work, reading and writing data items, and then it released a lock, taking it over to the shrinking phase, and from then on, the transaction can just release locks. So transactions can hold them. As long as they don't release a lock, they will remain in the growing phase until that first lock is released, and then we go to the shrinking phase. A transaction can also hold the locks all the way until the commit point. And this is how we prevent the dirty read problem. Basically, the whole lifetime of the transaction is spent growing until it reaches the very end of the transaction where it wants to commit, and then it releases all of the locks at one time. So the shrinking phase is very, very short. So again, this shape can be slightly different depending on how quickly the transaction gets its locks, whether or not it spends time doing work in between, and whether or not it wants to hold its locks until it reaches the commit point. Now let's look at an example. Here's a transaction processing example that we looked at in the transaction processing lecture. We have transaction A that would like to begin, read the inventory level in P200, write the inventory level in P200, and then commit. Transaction B would like to begin, read the inventory level for part 200, decrement that, and then write a new inventory level, and then commit. What we saw in the transaction processing lecture is that if these two transactions are not scheduled properly, we could be exposed to the lost update or the dirty read problem. So let's see how using two-phase locking helps address those two problems. In the first two steps, transaction A and transaction B begin. In step 3, transaction A applies for an exclusive lock on part 200. Why an exclusive lock? Because eventually transaction A will write to the inventory P200. It will ultimately update or change this item. Therefore, an exclusive lock is required. Now that the lock is accepted, transaction A can read the inventory level And here at step 4, transaction A learns that there are 10 items in inventory. Meanwhile, transaction B applies for a lock on the same item. Obviously, B will write to the same inventory item and it needs an exclusive lock. That lock request is denied. Why? Because A already has P200 locked. Therefore, transaction B enters a wait state. It is set up in a queue and it will be next in line once the lock on P200 is released. Meanwhile, transaction A continues. It decrements the items in inventory, and then it writes the new value out to the database. So at time 4, transaction A learned that the inventory level was 10. It took away 2, and then it wrote 8 back to the database. As a reminder, this value is dirty because it was written by a transaction that has not yet committed. This whole time, transaction B is waiting. Now, transaction A releases its lock on P200, and transaction A commits. The release of the lock and the commit happen together. Even though I've put it on 2 separate lines here, these two really happen very, very close together. Now, that value of 8 is clean because the transaction that wrote 8 to the database has committed. The other thing that happens, now that transaction A has released the lock on P200, now transaction B that has been waiting is allowed to proceed to get an exclusive lock on P200. So B has been waiting all of this time, and now it's allowed to go forward. Now that B has a lock on P200, it's able to read inventory, and at time 11 here, transaction B learns that there are 8 items left in inventory. It deducts 3, and then writes the balance back to the disk. Now we have 5 left in inventory. Of course, that value is dirty. Now transaction B releases its lock, and transaction B commits. So by using two-phase locking, transaction B is forced to wait until transaction A finishes all of its work. And this is how we ensure that the schedule of transaction A and B result in the correct value ending up in the database. Now let's look at a slightly more complicated example of locking. In this database, we have 4 items. We have the raise rate, we have Amy's salary, we have Bill's salary, and we have Carl's salary. And these are represented by RR, Amy, Bill, and Carl. You'll see these on the next slide where we show their initial values here. The raise rate is 5%, Amy's is $45,000, Bill's is $38,000, and Carl's salary is $51,000. Transaction A would like to read the raise rate, then read Amy's salary, apply the 5% raise, and then write Amy's new salary to the database. Transaction B would like to read the raise rate, read Bill's salary, apply the raise, and then write Bill's salary back to the database. Transaction C would like to read the raise rate and then write a new raise rate to the database. Then it will read Carl's salary, apply the raise, and then write Carl's salary to the database. So transaction A and B only need to read the raise rate. Transaction C will both read and write the raise rate. We'll indicate a shared lock with SL and an exclusive lock with XL. So the question comes up, what type of locks will each transaction require? You look at these 3 transactions, what sort of locks will they need? Exclusive locks, or shared locks, or some mix of the 2? So I invite you to pause the video at this point and maybe jot down a few of your thoughts. Remember that an exclusive lock is used when a transaction has to write to the database. A shared lock can be used when a transaction only needs to read a data item. Okay, here are some thoughts on the types of locks that each transaction will require. Remember that transaction A only needs to read the raise rate. Therefore, transaction A will need a shared lock on raise rate. Transaction A will ultimately write a new salary for Amy. Therefore, transaction A will need an exclusive lock on Amy. In a similar way, transaction B only needs to read the raise rate, so transaction B can get a shared lock on raise rate. Transaction B will ultimately write a new salary for Bill, therefore it needs an exclusive lock on Bill. Transaction C needs to both read and write the raise rate. Therefore, transaction C will need an exclusive lock on raise rate. And, of course, transaction C will write a new salary for Carl. Therefore, transaction C needs an exclusive lock on Carl. Let's see how we can schedule these three transactions. As I mentioned before, the initial values in the database are 5% for the raise rate, $45,000 for Amy, $38,000 for Bill, and $51,000 for Carl. As the three transactions begin, we note them here, transaction A beginning, B beginning, and C beginning. Transaction A goes first, and it acquires or asks for a shared lock on raise rate. Why a shared lock? Because transaction A only needs to read the raise rate. That lock is granted, therefore transaction A is allowed to read the raise rate. So at step 5, transaction A learns that the raise rate is 5%. Transaction B also asks for a shared lock on raise rate. Why? Because transaction B only needs to read raise rate. And this lock is also granted. Why is this allowed? Because shared locks are compatible with other shared locks. We know that transaction A is just going to read raise rate, and transaction B is only going to read raise rate. Therefore, transactions A and B can share this lock. A gets a shared lock on raise rate, B gets a shared lock on raise rate. Now we have transaction C. Transaction C asks for an exclusive lock on raise rate. Why? Because transaction C will try to change raise rate. And that lock is denied. So think about these three questions. Why are transaction A and B able to get a lock on the same data? Why was transaction C denied a lock? And what phase, growing or shrinking, is each of these three transactions in right now? Again, I invite you to pause the video and jot down a few of your answers. Okay, transaction A and B are able to get locks on the same data because they are shared locks. A and B only want to read the raise rate, so they can share access to that data item. Transaction C was denied their lock because transaction C was trying to get an exclusive lock on raise rate. Exclusive locks and shared locks are not compatible. So as long as any lock is in place on a data item, another transaction cannot get an exclusive lock. And as far as the phases, transaction A, transaction B, and transaction C are all in the growing phase. We know this because no transaction has released a lock. So when we ask that question, what phase, we want to know whether or not a transaction has released a lock. A, B, and C have not released any locks yet. Let's move on. At step 8, transaction A asks for an exclusive lock on Amy's salary. There's no other transaction that has a lock on Amy's salary, so that lock is granted. Why does transaction A need an exclusive lock? Because eventually transaction A will write to Amy's salary. So an exclusive lock is necessary. Now that that lock is granted, transaction A is able to read Amy's salary, and we learn transaction A learns that Amy's salary is $45,000. So now transaction A has all the information that it needs to apply a 5% raise to Amy's salary of $45,000. Meanwhile, transaction B, because it has a shared lock on raise rate, is able to read the raise rate. So at step 10, transaction B learns that the raise rate is 5%. Transaction B acquires an exclusive lock on Bill's salary. Why? Because eventually transaction B will write Bill's salary. So at step 11, transaction B learns that Bill's salary is $38,000. This allows transaction B to read Bill's salary and then write the new salary back to the database. So now at step 13, transaction B has written Bill's new salary. That's $38,000 with a 5% raise is $39,900. That value is dirty. I didn't actually indicate that here just to keep the presentation a little bit cleaner, but that value will be dirty for now. Going back to transaction A is allowed to write Amy's salary. It already has the exclusive lock. It did the math. 5% raise, $47,300. At this point, at step 14, A, B, and C are all still in the growing phase. As of step 14, no transaction has released any lock. Transaction A has two locks, the shared lock on raise rate, the exclusive lock on Amy. Transaction B has two locks, the shared lock on raise rate, the exclusive lock on Bill. And transaction C has been waiting. Transaction C has been waiting all of this time for raise rate to become unlocked so it can proceed. At step 15, this is the first time any transaction so far has released a lock. As soon as transaction A releases the lock on Amy, transaction A goes into the shrinking phase. So as of step 15, A is shrinking, B is still growing, and C is still growing. Now we've got the rest of the schedule. We know at step 15, A is shrinking, B is still growing, and C is still growing. At step 16, transaction B releases its lock on raise rate. And now, as of 16, A is shrinking and B is shrinking. C is still growing. Why is transaction C still waiting to get a lock on raise rate? Transaction B released its lock on raise rate. How come transaction C can't go? Well, the answer is A still hasn't released its lock on raise rate. So raise rate is still locked up and C has to wait a little while longer. At step 17, transaction B releases its lock on Bill, and then transaction B commits. So as of step 18, transaction B is completely finished. It began, got a lock on raise rate, read raise rate, got a lock on Bill, read Bill, wrote a new salary, released the locks, putting it into the shrinking phase, and then committed. So B is all done, transaction B is finished. At step 19, transaction A releases its lock on raise rate. As soon as that happens, transaction C is now allowed to go ahead and get its exclusive lock. Transaction C tried up here to get an exclusive lock on raise rate and was told it had to wait all of this time until step 20. And it had to wait for A to release the lock on raise rate. B had already released its lock on raise rate, but it had to wait for all transactions to release their locks. And then the exclusive lock is granted. Transaction A is still shrinking. Transaction B is done. And transaction C is still in the growing phase. Another question often comes up. Does a transaction have to release the locks in the same order it acquired them? And I invite you to look at transaction A for a minute. Look at the order in which transaction A acquired its locks, and then see if you can figure out whether A released them in the same order. And again, I invite you to pause the video for a few minutes and take a look at that. You can also look at transaction B and see if transaction B did things in the same order. Okay, if we look up here, we see that transaction A got a shared lock on raise rate first, then the exclusive lock on Amy. But when releasing, transaction A released its lock on Amy and then released the lock on raise rate. So the order in which locks are acquired and the order in which they are released doesn't really matter. The only thing that matters to two-phase locking is as soon as any lock is released, and it could have been the release of Amy's salary, or if we had released raise rate up here, it doesn't really matter. As soon as that's released, then the transaction goes into the shrinking phase, and it cannot ask for any more locks, any new locks to be applied. It can hold the ones that it has, but it can't release any. All right, I think we're in the home stretch now. As of step 20, transaction C is finally able to make some progress. It's given its exclusive lock. That allows it to read the raise rate and write a new raise rate. So now, as of step 22, the raise rate is 0.03. Transaction A commits. That's all finished and done. Transaction C asks for an exclusive lock on Carl's salary. That is granted. There's no one else that has Carl's salary locked up. That allows transaction C to read Carl's salary and write Carl's salary. So now we have the new 3% raise applied to Carl. And then transaction C releases its lock on Carl. Now, as of step 27, here's a new question. Suppose a new transaction, let's call it transaction D, arrived right now. It just started. Would transaction D be able to get a shared lock on raise rate? What do you think will happen? Pause the video and maybe jot down your thoughts. As of step 27, even though transaction C has released its lock on Carl, transaction C has not released its lock on raise rate. Therefore, if transaction D started up right now and tried to lock raise rate, it would not be allowed. That lock would be denied. Any kind of lock, whether it's shared or exclusive, would be denied. Once transaction C releases its lock on raise rate, then it's pretty much done and the transaction commits. Now any new transaction that comes in that wants to work with raise rate, Amy, Bill, or Carl can go ahead and proceed. Actually, transactions dealing with Amy and Bill could have proceeded after A committed or after B committed. But now, finally, raise rate is completely open and a new transaction can come in and read raise rate. So again, this is following the two-phase locking rule, and we can see that when two transactions are sharing data, they can proceed in parallel. If a transaction wants to update some data, then it has to wait. Here's some observations. A shared lock is compatible with other shared locks, so two or more transactions can get shared locks on the same data. However, a shared lock is incompatible with an exclusive lock, and exclusive locks are incompatible with other exclusive locks. So that's really one of the key pieces here. When a transaction has an exclusive lock on some data, no other transaction can even read what that value might be for that data item. So exclusive lock really does block out any other transaction from reading or writing. Transactions can lock data in any order and unlock in any order, provided they follow the two-phase locking rule. The concurrency controller sets up a first-in, first-out queue for each data item, so it's possible that several transactions can be waiting for a lock to be released, and they will get them in the order in which they asked for the locks. In the prior example, there was only one transaction waiting, that was transaction C. It was waiting for the lock on raise rate to be released. Now let's look at a slightly different organization of transactions. Here, transaction A would like to read P200 and write P200. Then it would like to read P300 and write P300. We have a transaction B that's going to start by reading P300 and then write P300. And then B will continue to read P200 and write P200. What happens when these get started? Transaction A can begin, transaction B can begin. Transaction A gets an exclusive lock on P200. That lets transaction A read P200. Transaction B gets an exclusive lock on P300, and that lets transaction B read P300. So both A and B got started. What does A have to do next? Well, A is going to eventually write P300, so A needs an exclusive lock on P300. But it has to wait. Why? Because transaction B already holds that lock. No problem, let's let transaction B continue. Well, the next thing transaction B has to do is get a lock on P200. And can it do that? No, because transaction A has P200 locked up. This is a situation we call deadlock. Neither transaction A nor transaction B can make any progress because A has something that B needs and B has something that A needs. So they will be stuck in this situation pretty much forever. So what can we do about this deadlock situation? There are two main strategies to deal with deadlock. The first is to prevent deadlock from happening in the first place, and the second is to detect deadlocks and to break them. Prevention is a little bit of an extreme position to take. Basically, we say, to prevent deadlock, abort any transaction that requests a lock already held by another transaction. This is sometimes called the no waiting protocol. So if we think about it here, as soon as transaction A tried to get an exclusive lock on P300 and was told it would have to wait, we abort transaction A. And that, of course, would let transaction B continue. That is pretty extreme, though, because anytime two transactions have a conflict, that is, they're trying to work with the same data, and one of them is going to be writing to the data, then one of those transactions is going to be aborted. And that might not necessarily be the best thing for transaction throughput. What typically happens is we follow the second protocol, which is to detect deadlocks and then break them. In order to detect a deadlock, we can create what's called a wait for graph. In this graph, we represent each transaction as a node, and then if a transaction is waiting for another transaction to release a lock, we draw a directed arc. In this arc, we're saying that transaction A is waiting for transaction B to release that lock on P300. At the same time, transaction B is waiting for transaction A to release its lock on P200. Then we can traverse the graph, and if we find a cycle in the graph, and this could be between 2 transactions or 3 transactions or 4 transactions, if we find a cycle, then we have detected that there is a deadlock. 2 or more transactions waiting for each other in order to proceed. Once a cycle is found, we can then choose a victim. One of these transactions needs to be aborted so the other can continue. We could choose this randomly. We could choose this based on when the transaction started. For example, aborting the youngest transaction that has most recently started. Or we could look at the amount of work that they have to get done. If transaction A has finished 8 out of 10 steps, and transaction B has finished 1 out of 10 steps, it might make sense to abort transaction B because it really hasn't done that much work, and transaction A is closest to completing. Now we can wrap up the concurrency control topic. The concurrency controller is part of the DBMS software. It basically controls when a transaction is allowed to read or write. Locking is one popular concurrency control technique, But there are also techniques like timestamping, multi-versioning, and optimistic concurrency control. The type of locking that we focused on here is called two-phase locking, which has two phases, growing and shrinking. Growing phase when a transaction acquires its locks, and the shrinking phase when the transaction releases its locks. If every transaction follows two-phase locking, the resulting schedule is serializable. But we don't get anything for free. Even with two-phase locking, deadlock can occur if two or more transactions are waiting for each other to release a lock. And we talked about a couple of techniques to either prevent deadlock or to detect and break deadlock. That's all the material I have for concurrency control for today. As always, additional notes on databases and data warehousing can be found on my website. Thanks for watching, and I will see you in the next video.